In very recent times, my niece was trying to spin me on a tire swing. Unfortunately, my niece is not very good at spinning people, so I decided to make it a little easier on her. When she was spinning me, I had my arms all stretched out. So once she finished spinning me and let me go, I pulled my arms in. And as soon as I pulled my arms in, I started spinning faster. And the reason why is because the further your mass is spread from the axis of rotation, the harder it is to spin. So I had her start spinning me while my arms were all spread out, and it was harder to spin, so that when I pulled my arms in, the effort that she'd put to spin me was kind of multiplied a little bit. It was now easier to spin than it was when she started spinning me, so I started going faster. And this idea is going to help us understand the moment of inertia. So the moment of inertia is going to measure how hard it is to spin. A higher moment of inertia means it's harder to spin. And the moment of inertia will be given by, it'll be given about a certain axis. And for a given axis, let's say the x-axis, it's going to be given by integrating your region. Well, I want to see how far the mass is from the axis. So the distance from the axis, or at least the distance squared, is going to be given by y squared plus z squared. And then I can check the density of how dense the object is that far from the axis. And if I integrate the density times the distance from the axis, that's going to get me the moment of inertia around that region. And this should actually be about a region, or a solid, not a disk. About the y-axis, it's a similar story. Now my distance from the y-axis is going to be given by x squared plus z squared delta xyz dv. And about the z-axis will be given by the y squared, or x squared plus y squared over times density. Times dv. Like we used the moment, the first moment, or the moment that we looked at earlier, to find the center of mass, we can use this to find what we call the radius of gyration. And basically, the radius of gyration is given by the moment, or the square root of the moment of inertia about that axis divided by the mass. And that's it. And again, this is going to be the radius of gyration given by, or for a particular axis. And like the center of mass told me, if I put all of my mass at a certain point, how would the seesaw balance essentially? This is telling me if I put all of my mass a certain distance from the axis, this distance from the axis, how hard would it be to spin? So it's going to be a similar idea to the center of mass. So let's go ahead and use this to find the radius of gyration for the unit box with density x about the z-axis. These should all be triple integrals, is a good time to note that. Whoops. Oh well. So there we go. So we are going to calculate the triple integral of the unit box. We're actually going to calculate the square root of the unit integral of the box. We're about the z-axis, so I'm going to have x squared plus y squared times my density function. My density is given by x dv. And that's all going to be divided by just the mass, which will be x dv. So how are we going to do this? Well, I can start by finding this triple integral. Since we're doing the unit box, everything's going to be from 0 to 1. My function is going to essentially be x cubed plus y squared x. And just to, get it over with, we'll do z first. Well, actually, let's do x first. Just because I have a lot of x's and then, some stuff will go away. We'll do x, then y, then z. So that's going to be the integral from 0 to 1, the integral from 0 to 1 of x to the 4th over 4 plus x squared y squared over 2, integrated from 0 to 1, dy dz. Be the integral from 0 to 1, the integral from 0 to 1. This will just be 1/4 plus 1/2 y squared. Dy dz. This integral is just going to be 1/4 y plus 1/6 y cubed, evaluated from 0 to 1 dz. That's going to be the integral from 0 to 1 of, this will just be 1/4 plus 1/6. 1/4 plus 1/6, I have to think about a little bit. That's 3 over 12 plus 2 over 12, that's 5/12 dz. And the integral from 0 to 1 of 5/12 is just going to be 5/12. So that is my moment of inertia. And now I'm going to divide that by the mass. The mass is just going to be the triple integral of now just x, dx, dy, dz. That's going to be the integral of 0 to 1, 0 to 1, x squared over 2, from 0 to 1, dy, dz. That's just going to be the integral from 0 to 1, the integral from 0 to 1. That'll be just 1/2 dy dz, which will be the integral from 0 to 1 of 1/2 dz, which will just be 1/2. So the radius of gyration about the z-axis will be just the square root of 5/12 over 1/2, which, if you simplify, will be the square root of 5/6. That would be the radius of gyration. So that basically says you could just take a point with the given mass, which ended up being 1/2, and you could take a point with mass 1/2 and put it square root of 5/6 units away from the z-axis, and that would spin just like the box would spin. So there you go.